No.
So now, suppose you think of rolling a die. What are the possible outcomes? 1, 2, 3, 4, 5, 6. If you plotted, what is the probability of getting 1 by 6? Probability of getting 2 is 1 by 6, 3 is 1 by 6, 4 is 1 by 6, 5 is 1 by 6, 6 is 1 by 6. So if you plotted these probabilities on the y-axis and x1, x2, x3, x4, x5 on the x-axis, you will not get a bell-shaped curve. You will get a straight line. Right? Okay. Now, so let's try to do that. Okay? So let's try to do that. So wait first, let me write a program. Okay? So I start a new program now. New script. Okay? The sequence. So data say is equal to sequence. Yeah. So what is data? 1 to 6, right? If you print it out, you will get 1, 2, 3, 4, 5, 6. Now think of sampling from this population. Right? Think of taking a sample of size 1000 from this population. Okay? Think of taking a sample of size 5000 from this population, and then let's plot the probability distribution of that sample. Okay. So, we'll go here. Okay, so S is equal to sample from the data 5000. Let me write what S is. Yes, so S is these 5000 numbers have been chosen at random from 1, 2, 3, 4, 5, 6 with replacements. You can choose 5000. Pick one, put it back, there's a chance of being picked at. Right now, let me plot the probability density of S. Plot density S. Okay? Right? If you prefer more colorful picture, let me make it red for the time being. So you see here this picture. Right? Okay? Not normally distributed. You actually should be probability of getting 1 is 1 by 6, probability of getting 2 is 1 by 6, 3 is 1 by 6, and so on. Right? So you get a flat line here. Now, let me change this a little bit. Let me say that I have got one sample of size 500. Let me take another sample of size 5000. Okay? Sample data 5000 replace is equal to true. Okay? So S is one sample, S1 is another sample. And think of the probability distribution of S plus S1. Yeah, think of the probability distribution of S plus S1. Okay. See. This is looking more bell-shaped, not entirely. It's still wiggly. Obviously, because this will take values between 0 and 12, 1 and 12. This taken values between 1 and 12, but it's more approximating the bell curve, right? But not entirely the bell. So let me now take an S2 as well. Okay, let me call this S3. Also let me call this S2. Yeah. It has slowly started to smoothen out. Right? The wiggly parts are going away. Right? Okay. So now let me make it S4 as well. S2 plus S3.
are we actually doing?
What we are actually doing is, we are taking a sample of size 5000 from a population not normally distributed. We saw that that is not normally distributed.
5,000 random numbers we are taking.
No, we are taking from the, we are not taking 5,000 random. We have got 1, 2, 3, 4, 5, 6.
Okay.
From that we are choosing 5,000 numbers at random
Oh.
with replacement.
Okay.
Right? So we saw that if you just do it once and plot the problem distribution, it's not normal. It's got wiggly. If you take another sample and add the two samples and take the problem distribution, it is not as wiggly. It is more bell-shaped. If you add 3 more, the idea is if you keep on adding these samples, the distribution now is becoming more and more bell-shaped, right?
Okay.
Okay.
So instead of adding, can we increase the sample data? Like instead of
No,
5,000?
no, just by increasing the sample will not be. So, for example, if I just keep it S here,
Yeah.
let me just let 5 and let me make this a very large sample. Alright? Then see what happens. The shape is not changing, right? Okay?
How about adding polynomial like to the base to the power to the
No. So S, so let me write S raised to 5. Not normal, right? Okay, because, right, so let me, so if I keep on adding here S plus S1 plus S2, now let me make it, so let me send this back to 5,000.
What is that replace T? Every time it's replacing S1, S2, S3.
No, it's a sampling with replacement. So I've got 1, 2, 3, 4, 5, 6. After this I have to take a sample of 5,000 times. So idea is if I chosen 1, I put 1 back again and 1 becomes available for reselection again. That's sampling with replacement. If I say once I've chosen 1 is not available for replacement again, then that's sampling without replacement. Yeah? So it is sampling with replacement because otherwise out of 1, 2, 3, 4, 5, 6 we can't take an infinitely large sample. Right? So S1 plus S2 plus S3 I add, right? S plus S1 plus S2 plus S3. Right? Now see what happens. It's looking more normal. Right? Now in fact, if I keep on adding, if I add another S3, effectively, instead of doing an S4, I just add another S3. Right? And let me add another S3. And let me add another S3. And let me add another S3. Right? Then see what I get. Yeah? It is now slowly, the point is, as I keep on increasing the number of times I am picking up S, okay, right, S3, or no, I need to have actually different samples this time. So S1 plus S2 plus S3. So I need to, I have an S4. So this is S4. S3 plus, if I add S4, I put S5, S6, S6, okay. Yeah, now you see it's becoming slowly more and more normal. Alright, it's not exactly normal as yet, but if I keep on adding numbers like this, so if I have another here,
So question, when you added the same variable again and again, and when you added different variables again, it made a difference.
it made a difference because I was adding the same thing, right? I was adding the same set of observations, whereas the idea is to take a fresh random sample every time.
Okay.
Okay, when I'm doing S6, so let me just explain to you what I'm doing once I'm, if I do this S7, if I do this S8, and if I do this S9, I promise you this will get done all this time.
What is the 5,000 in that?
5 is the number of data points it picks. It is picking up some data at random, no?
Between 1 to 6.
1 to 6. So it's taking up 5,000 times those numbers at random. S7 plus S8 plus S9 plus S10. Okay. Now you see. So it's becoming more and more and more normal. Right? The wiggly parts are going away. And if you keep on doing this, eventually it will keep on approximating normality. So this is a part of a very important theorem. This theorem says that even if there is a population which is not normal, okay, if the population is not normal, if that population you take one sample, the product distribution of that sample will not be normal. But if you take two such random samples and add them, the sum will be more closely normal, close to normality. If you take three random samples from a population which is not normal and add the three, the sum will be even more closer to normality. And the larger the random the samples that larger the number of samples that you add, the closer you get to the normality for the distribution of the sum. Right? For the distribution of the sum. Right? Which is a theorem called the central limit theorem. Okay, which says that even if if the population is not normally distributed, the sums of random samples from the population will tend to be normally distributed as the number of items you have summed keeps on increasing. And the approximation will get closer, the larger is the number of the sum that you keep on adding. Right? Sure? Is this idea clear?
Just one.
Yeah.
You mentioned the last one that for the distribution of the sum, when you say distribution of the sum, do you mean by the spread across?
No, the probability, the whole shape,
Oh, okay.
whole picture.
It should look like this. No,
Yeah, so what you will do is, you will actually find here that if you keep on adding these, no? Right, so if I again, so if I were to take this, and if I put here, and if I were to say 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So let me keep on adding from this. S10 plus S11 plus S12 plus S13 plus S14 plus S15 plus S16 plus S17 plus S18 plus S19 plus S20. Okay? Right? This is becoming more and more bell-shaped, you see? Right? It's becoming more and more symmetrical, more and more bell-shaped.
So, sir, if even I have a data set, large data set, do we need to sample every time?
No, you don't need to sample every time. This is just a theorem which is going to be important for you. This is just a theoretical result which is going to be very important for you. Because the question that we are trying to answer, now the question that we are trying to answer is, the normal distribution is one of the many distributions in statistics. There's the normal, the binomial, the Poisson, there's all sorts of distributions. So why privilege the normal distribution? Why are we going to study only the normal distribution now? And the picture that you are now getting will give you the answer. It says, see, if you just do plot density, say S1, okay? If you just plot the density of S1, right, you get a picture like this. Is this normal? No. Probability of getting 1, probably getting 2, probably getting 3, probably getting 4, probably getting 5, probably getting 6. Right? Okay? In fact, if I increase the sample size, the only thing that would happen is, so this is S1. Okay, if I increase the sample size for S1, you must now tell me how the picture changed. Okay, suppose I did that, say, I did this a really large number. Right? Okay, so this is the whole thing, and I then plot this density.
So sample.
So the pictures become like this. Now can you tell me why the pictures become like this? The only thing I have done is for S1 I have increased the sample size. Previously the picture was like this, wiggly. Now it's become more, yeah, it's become more sharp. Why?
Equal probability of getting one.
Yeah. But what has the sample size to do with it? You see, my random variable is a discrete random variable, right? So it really only takes values 1, 2, 3, 4, 5, 6. It doesn't take any values between 1 and 2 and 2 and 3 and so on and so forth, right? What I'm estimating in my picture is the probability with which it takes the value 1, probability it takes the value 2, probability it takes the value 3, probability it takes the value 4, probability it takes the value 5 and so on and so forth. Now as the sample size increases, these probabilities get better and better approximated, so I've got the probability mass function at 1 and nothing between. Right? So if I keep on increasing the sample size, all that will happen is these peaks will become more and more thinner. Right? So that's the only impact of increasing the sample size. So for example here, if I S1 was, if I put say 2 more zeros here, or these more zeros, right? And then if I just run this here up to here, yes, you have really narrow kind of, hopefully it's done this. Yeah. Okay, you get really these very narrow kind of bounds. But the distribution has not become normal. Now, on the contrary, on the other hand, see now what I am doing. So let me set this back to, okay, say something actually it won't matter, but if I just set to 5,000. Now, S is one such sample, S1 is another, S2 is another, S3 is another, S4 is another, S5 is another, and so on. So I am taking many such samples, each of which is not normally distributed, and I am adding them. Right? And I am now seeing what is the sum. What is the distribution of the sum? Each of these is not normally distributed randomly. Right? If I add them, so I am looking at the distribution of the sum, and you see, the distributed sum is much more normal. Right? It's much more symmetric, bell-shaped and all that. Yeah? And if it's not perfectly symmetric and bell-shaped, but I can assure you that if you kept on adding these variables, you'll keep on becoming more and more bell-shaped, and as you keep on adding more and more of these variables, okay, as the sum becomes larger and larger, sum has more and more components, the number of components in the sum keeps on increasing, the distribution will get closer and closer to the normal distribution. So therefore, whatever the distribution of the original populations, if you take a random sample of size n, and if you take many such samples and add those samples, the distribution of the sum will be approximately normal, with the approximation becoming better and better as the number of items you sum increases. Right? Therefore, the normal distribution is an important distribution for us, because it is a limiting distribution of the sum of any random variables, whatever their distribution. This is okay? Right?
Meaning if the samples are not randomly distributed.
The population is not randomly distributed. Not normally. Everything is randomly distributed. The population is not normally distributed. But if you take random samples from this population, each of these samples will also be not normally distributed. But the sum of these samples will tend to be normally distributed, approximately, with the approximation becoming better and better and better as the sample size becomes bigger and bigger and bigger. As the number of times you add, number of items you add keeps on becoming bigger and bigger and bigger.
For that, but sample should be same. The number of
Not same.
as you said, the sample is 5,000. So
No, in the sense, you see, I will not be able to add. No? If one is a sample of 5,000, the other is a sample of 20,000, then I will not be able to add them. So that will be the same size, because I am going to add. No? Otherwise addition will not happen. That's the only reason. Right? But whatever, if this is only size 50, even then the same theorem will work. Right? Even if I make this a size 50. Okay? Because what matters is the number of items I am adding, not the sample size. Okay? See if I just make this 50. Okay. Let me make all of these 50.
50 items in that sample.
Pardon?
50 random.
So 50 observe 50 random samples I am taking. 50 items in each random sample. And like that I am taking 20 samples and adding them, 20 or 21. Yeah. So if I do this,
So this will also have the decimal values as well.
pardon?
Decimal values.
No, because each one is an integer.
Discrete.
Each one is a discrete variable. If I add, the resultant is still a discrete variable. But my distribution now becomes a continuous variable.
So for taking the discrete values, did you mention there any command for that? Or?
No, I said let data be a sequence of 1 to 6. Right? So if I run this, and if I get this, so this is my population. Right? This is my population. This is my population. 1, 2, 3, 4, 5, 6. Right? From this 1, 2, 3, 4, 5, 6, what did I ask the computer to do? I asked it to take a sample of size 50. So there will be 50 numbers chosen from this 1, 2, 3, 4, 5, 6. Okay. And now, so suppose let me run this. Okay. Let me run this. Let me run this. And let me run this. You see, it's still bell shaped, no? Right?
So if it's bell shaped, so what does this mean? Like there's a higher chance where the peak is, or?
No. All that means is that it gets closer and closer to the normal distribution.
So does it mean that the maximum of the values are closer to the mean? Something like that?
Nothing. Nothing like that. Like I'll tell you, have you seen a normal distribution, how it looks like? I'll just draw a normal distribution. Okay. Say, let x be normally distributed numbers, random numbers normally distributed, very large number of randomly distributed, okay, with say mean 0 and say standard deviation 2. Okay. So x is, with this command, R will generate normally distributed random numbers which have mean 0 and the standard deviation of 2, the spread of 2. Right? Okay. So suppose I now, and if I plot this, plot. Yeah, plot density x. Okay? See, this is the density of the normal distribution. What is the mean? 0. This is determined by the variance. The standard deviation to the variance must be 4. Now suppose if I change this, suppose I change the mean to say 10. Okay? How will the picture change?
Positive.
I was told that this curve should never touch the axis.
Yeah, it should actually not, but in this graph it does. So it should actually, because all that happens is around after these points, the values are incredibly so small.
But it seems like they're touching, but they're not touching.
Yeah, but they're actually not touching. Graphically it's seeming as if it's touching, right? Because those values are incredibly small because it's a minus infinity to plus infinity kind of a curve. But this expresses the probability that the x variable takes a particular value. Probability x takes the value 10 is about this, 0.2 or something. So probability with which this random variable takes values less than say 4.5 and on are so small that in the graph they look as if the graph is ended, but actually no, right? Like similarly here, suppose I change the mean. So what has happened when I change the mean from say -1? If I change the mean to -1, what's going to happen? The whole graph will shift to the left. Yeah, the peak is now here at -1. Right? If I set it to 0, if I set this to 5, yeah, the whole graph will shift to the right. Yeah? But now, if I change, now let's look at this graph. See where the values are. Most of the values are between 0 and 10. if I change the standard deviation from 2 to say 6, the graph will the mean still continues to be 5, but the spread of the graph has increased. Right? Okay? Now, the point that we are trying to argue here is that even when each of these S, S1, S2, S3, S4 are not normally distributed, they are all wiggly kind of. If you keep on adding, then the probability distribution of this sum will get closer and closer to this general shape as the number of items you add keeps on increasing. Right? So the normal distribution can very often be looked upon as a limiting sum, limiting distribution of the sum of non-normally distributed random variables. And that is why it's an important distribution to us in statistics. Right? That's why we use it. So even if you don't know, say for example, the distribution of, so think of it. Suppose think of the income in Mumbai. Is income in Mumbai across households normally distributed? No. Perhaps it's something like this, right? Where there are some very poor people and then there is a bulge in the distribution and it spreads out. But suppose I take a sample of size 100. So if I have x1, x1 is a random sample, x2 is another random sample, x3 is another random sample. They are all samples of size 1. Each of them are not normally distributed. But if I take summation xi, that will be more approximately normally distributed